So we have with us Patrice and Bob, and they're going to talk about the CAP.js database adapters, deep dive into how to leverage the CQN and as well the CDS REPL, which seems to be the theme of today, which is awesome. So hand it over to them. Have fun.
Yeah, welcome. So with the last recap in CDS 8, we have added 3 new database plugins. We have CAP.js, HANA, SQLite, and Postgres. And now with CDS 9, it's mandatory to switch to them because the old database implementations are removed. And we will go through some basic information, high level, and then also some REPL interactions to show the power that that the new databases give you, where in the past it was only allowed to use some of the features on HANA. Now both SQLite and Postgres can do the same thing as the HANA driver can do. I'm going to give a quick overview on our principles when we came up with the new architecture for the databases. And one of the primary things that we keep in mind when developing the database is to not look at the data. Because when we look at the data, we cannot predict how we're going to perform. So when we process your query, we only look at the query. If you're doing inserts or when you're selecting, we don't look at the data. So this allows us to provide streaming features like writing streaming or reading streaming. And it also allows us to just save a lot of resources. Because your application might be looping over the data. We do not want to loop over it one more time just to make some small adjustments to it. Next thing that we keep in mind when we develop these databases is that they are consistent amongst each other. So if you want to develop on SQLite and production want to switch to HANA, there is a very little chance that they will behave differently. There will always be certain differences that we cannot control that are based upon the database itself, like transactions. But overall, we make sure that when we run a test, that we can run it on all 3 databases without differences. And then the last thing that is very important to us is feature completeness. So if you might need a feature that HANA supports but SQLite doesn't support, that we give you compatibility capabilities. So we have some functions that work on other databases. These are mostly based upon the OData protocol. But we also have a few HANA functions that we re-implemented for Postgres and SQLite that you can use. And then Patrice will go into an actual demonstration, right?
Yeah, thanks, Bob, for the introduction, and nice to see you all. Pretty packed room today. I want to talk about path expressions in general today with you, which is like an inherent feature of the CAP framework in general. And I would say, generally speaking, path expressions in CAP are a way to navigate along structured elements and or associations. And yeah, to show you how that works, I want to do a little live coding session with you. For this, I have prepared a bookshop. I mean, it's just a standard bookshop, but I have added some extra data to spice things up. And okay, yeah. So this happened before. Okay, now I'm just in my command line. You can see I'm in my bookshop, and we will just start the REPL session. With the nice --run command, we can bootstrap the environment so that we have easy access to our entities through this JavaScript variables. And let's start with the most basic form of a path expression, which you should definitely use, because in its most basic form, path expressions will help you to get rid of handwritten joins. For example, if we would want to select all the books, right, just the title, and then also the author name, you don't have to do a join with the author table to get to the name property. You can just travel along the association to get a desired result, and you see we get the expected result structure back with the title alongside the author. And obviously, under the hood, this is not magic. We transform this stuff for you, so you don't have to take care of those nitty-gritty details. As you can see, obviously, a join was generated for you in the background with a proper on condition. So don't do this by yourself. This is the most basic form of a path expression. Now, let's see how we can further leverage this feature. And next thing I want to talk about is the exists predicate, which is I would say, pretty famous in SQL and also throughout the CAP environment ecosystem. However, I want to show you some nice tricks how we can further spice up the exists predicate with some nice features alongside path expressions. So first, let us insert an author which has not yet written any book, so that we can do some nice existence checks here. This is now just myself. I've inserted myself into the table, so now we are good to go. And I want to show you how we can now, in the most basic form, we want to select all the authors, right? This time just the name where exists books. This is, I would say, very nice declarative syntax here. You don't have to fiddle around with doing a subquery by yourself and doing the proper semi-join here. Again, we do this under the hood for you. And we get back all the authors, but not myself, because I have not yet written any book. We can just prove my point by negating the whole expression. And now we only get Patrice back, who has not yet written any book. Maybe someone, but certainly not today. And yeah, so this is the most basic form of the exists predicate. I want to now show you some lesser known features. For example, if you want to spice up the condition for the existence check, right? We can go ahead and use those square brackets here, which we call infix filter notation. And what I can do in here, I can use another path expression. For example, if I only want to select authors which have written a book of a certain genre. For example, my favorite genre is obviously fantasy. So I say square brackets open genre.name, which is another travel along the genre association within the books table, right? And if we do that, we only get 4 authors back in this case, right? So in the background, we generate a join for the subquery. I will show you that later on, which makes sure that the genre name of the book is considered. And we can even spice things further up. If I go into the infix filter after our implicit where condition for the subquery, we can add, for example, further modifiers, query modifiers, like a group by clause. We can say group by author.id, and then even we can use aggregations in, for example, the having clause here to check for existence of authors which have at least written 3 fantasy books. In this case, those 3 guys and girls have written at least 3 fantasy books, right? And now I want to jump out of the REPL real quick to have a look at the things which go on under the hood. And you can see the gist of the SQL we sent to the database for the CQN I just showed you. And in the top 2 lines, we can see obviously the select for the author name, and everything else is what you have written in the infix filter. And we see the subquery has been generated for you. First thing which comes to mind in line 8 is the semi-join to correlate the authors with each book, right? Then we have the inner join, which matches only those books which have a genre name that equals our placeholder here. In our case, it was fantasy. And finally, in the last 2 lines of the subquery, we can see the group by and the aggregation in the having clause, right, to make this thing work. And it is as simple as that, very declarative. You could even go ahead and move this whole stuff to the from clause, which is another syntactic variant of this. You could also, for example, specify query modifiers in here. For example, if I would want to order by the author name descending, right? So just some nice lesser known features here around path expressions. The next thing I want to talk about is the topic of nested projections. Nested projections can be used to retrieve complex document-like data from the database with a very nice declarative syntax again. And to show you what I mean, I will just start another query here. For example, if you would want to select, again, all the authors, right? I open the projection. Again, we select the author name. But this time, we also want to query for all the books this author has written. So we can just use the association books, curly braces open, books, what do you want to know about the book, the title, and we can also travel along the genre association to the genre name of each book in here. And it is as simple as that to get a nice result structure back in JSON format here. You can see, for example, J.K. Rowling and her books she has written comes back as a JSON array in here with a record representing each book, right, she has written. And this is not all. We can even go ahead and spice things up again with some additional path expressions. I can show you what we can do now. For example, if I would want to only select all the authors, let's say which name equals Brandon Sanderson. Who knows Brandon Sanderson here? Nice. It's my favorite author. Very nice. I would recommend every fantasy fan to look into him. And for example, this time we only want his books, right? So we do another projection here, but not all of his books. We can, before we open the nested projection, we can again use the square brackets infix filter syntax to check for certain attributes here. For example, I can use the starts with function. Bob has teased this. Just to check for books which have a title that starts with Mistborn, for example, right? And we can even specify further arguments in here. We can say order by title, as has been shown before, and maybe limit the result to 3 records, which is the first trilogy in here. And then we can say, okay, we want a title and again, the genre name, okay? And then I have to close the projection. Everything looks good here. I have syntax error here. I don't want to type this whole thing again, so I just copy it real quick. I'm prepared, hopefully. Give me a sec. Okay, here we have the same query again, this time in a proper way. And we can see we get back our author, our desired author, which has the books which we wanted. Just the first 3 books which have a matching title. Really recommend this trilogy to everyone. So next up, I want to show you that we actually do only one query in the back, and as you have seen, we get a record back which is not easily achievable in pure SQL. For example, if you would want to retrieve books in a SQL column, it would not work because, as you can see, the books is a too-many cardinality, and we cannot squeeze all the books into one column with a single SQL query. Actually, you can do that. We will show you how. How we do it for you. You should not fiddle around with this by yourself. Just use our declarative syntax for this. And I want to show you an example where we have a deep query in here. It's kind of like the hierarchy example Daniel showed in the keynote, right? We select from the genres. Each genre should come back with its name, but also with the parent genre. And again, the parent genre should also include the name, and the parent genre, so to say, the grandparent genre, should also include the name. But this time, we only want genres back where a parent name equals fiction, right? Okay, so we can fire this query. We get all the genres back which have a grandparent genre that equals fiction. Quite some in here. And yeah, what happens under the hood? I would like to give back to Bob, who will give you some insights in how that works.
Yeah, so if we go to the next slide, then we should be able to see here the SQL statement. This is the actual SQL statement that we run. It's a bit bloated because what we are doing here is we're calling JSON functions to actually transform the list of entries into a single scalar, so that SQL accepts it again as a subselect. So what's actually going on is we're basically making a bunch of subselects to get the children or the parent in our case, and stick it together into a single row. And then in the bottom half here, you can see we are doing the joins. And that join is to find the parent name. So the subselects, if we did not have the where class, we would still have this exact same subselects, but we would not have the two joins at the bottom that are there to do the name comparison. And because we can run this as a single query, you lose network overhead and like compile time and post-processing. Because as mentioned at the start, we do not want to look at the data. So normally what we did with the old databases, we would run one query, get the root entries, run follow-up queries to get parents or children and all these relationships. And now we just send one and tell the database, this is what we want to get back. And that is also what we can then return in the end. I also wanted to show that in a more detailed example, where we are using streaming APIs to really show that we're not looking at the data. And so I prepared also the bookshop. I went and got from an open source project. I got all the authors that they have and all the, they call it works, but we call it in our case books. So I got all of these and I uploaded them to HANA and to SQLite. It's a few gigabytes in total. And what we can do is we can do a little modification here to the admin service, and we can hijack the OData protocol. So normally you don't need to add a read handler, but here I added one for all of the entities. And the most important part here is I do rec query.pipeline. So normally we would not do this. Normally we would just execute it and then return it to the OData protocol. But here I just pipe it directly into the request response, and I need to flag that it's an application JSON. So when I do this, I can go into any browser and then fire basically any query I want against this application. And then you can see that we get our data back in a structured way because I didn't expand on the books. And I modified it. I modified the service so that I can go over the normal limit. I just put a bunch of zeros in there. And then I have to actually switch from the browser to command line to even be able to show the performance that this has. Because if I would run this query with more and more zeros in the browser becomes the bottleneck in downloading the data instead of the CAP application itself. So if we have a look here in the bottom right, I will fire my download query, and using curl, it takes a little bit of thinking to get it prepared, and then it will start downloading it. See whether maybe my HANA went down. So it will start downloading it. You can see here how much megabytes of data we're pulling out of that system. And normally, if you would try to load this into the Node.js application's memory, it will go down. So we can modify the query to whatever we want it to be. We can remove the expand. We can increase or reduce the top to whatever we want it to be. So if I go take it a bit down, then you will see it will be so fast we can't even measure, like at sub-second response times for megabytes of data coming back. And this is especially useful for applications that want to allow to export Excel sheets or things like that without putting actual load on your application service. And then we can also show that this is not just for HANA, right? So if you're development and you're SQLite and you have your nice 9 gigabyte SQLite database file, you can go and say the exact same thing. I want to get the top 1,000 authors and all their books, right? And there you see sub-second, 5 megabytes. We can add some more zeros. It doesn't go too high, but it will go pretty far. And it's not stressed about these requests at all. It's I put it on the wrong place. It's live, right? And then SQLite will also do it I think it takes 9 seconds or something like that to get the whole half gigabytes of authors downloaded. But if you would try this with the old database services, you would not have a chance. The application would just hang and crash. So these kind of features, they will be used over time behind the scenes by the platform. So once you're using OData and you don't have post-processing, so no on-after handlers, we would automatically switch to pipeline because we don't want to put extra load on your application service. We push everything down to the database. And it also works for writing. So here I have a little example that I use to upload all this data. And it basically comes down to this single line here. Everything else is just me looking for the files. I just say, give me a read stream of the file, insert it into my target entity, and then we just wait. It takes always a little bit to do. But yeah, we could upload this to SQLite and HANA within like 5 minutes, which if you have more than 10 gigabytes coming in per 5 minutes, you're gonna have other issues as well. So this should be a good baseline. And that's basically what we wanted to show.
That's right. Let's go back to the last slide. Do we have time left? Okay. That's fine. Can always approach us for more.
All right. Big round of applause. We do have time for 1 or maybe 2 quick questions from the audience. Anybody?
First, thank you for the talk. It was really good. One quick question about the JSON SQLs. Is there an easy way to debug them? Because they are always a pain to copy out and figure out what is the actual statement so that we can then look at, for example, the HANA optimizer where it's stuck.
Yeah, the main thing is that most of the SQL statements are going to be boilerplate, where we just have to tell the database how we want the data to come back. Once you get used to the pattern, you can easily just delete it out because I think Patrice as well.
But do you plan to have an option to remove the boilerplate in the logging, for example, so that then you don't have to do it?
Yeah, we had it at the start with a kind of hacky way, which caused more trouble than it solved. One thing that you can do is switch to SQLite, where it's much more simpler. We're also considering to make a debug service, which will print without boilerplate, like idealistic SQL statements, effectively.
Yeah,
Right,
that's a good point.
everybody.
But basically, all of this is boilerplate code, and the real query is just this one in here.
You're not sharing.
Ah, okay. I'm sorry, guys.
All right. Thanks, everybody. And we have upcoming in this room